Yeah, actually, very sorry. There was a sort of disturbance that came up in the computer, so I had to re-log in back. Let me just present my screen. Yeah, like, can you just tell me where I actually stopped? Like, uh, is it that you were unable to like get the things from the start, or was did oh, okay, okay, okay. Okay, let me just present my screen and then is my presentation visible? Ah, okay, yeah, sure. So, you were able to like listen. What do you say? You were able to follow up till here, right? This windmill types and characteristics, or yeah, okay, 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 fine, fine, fine. Then I can understand where. So, let me just try drawing the airfoil structure. So, this is so. Can you? Yeah, I hope you will be able to see my Jamboard. Yeah. So this is actually your airfoil structure. So if the diagram is more neat, then it will be somewhat like this. So this is your airfoil structure. The blades that you actually have in your windmill is supposed to consist of this airfoil structure. The reason why we use this airfoil structure and what is its importance is, so this airfoil structure has something called as a cord. So this is a cord that basically runs along the in the middle of your airfoil. So uh, uh, higher the thickness to that of your cord ratio, the lift force will be high. So the lift force is nothing but it is basically the force that is acting perpendicular to the direction of the airflow. So in this airfoil, once you have a higher thickness to the chord length ratio, the lift force will be high. So as the lift force is high, it will be generating more wind power. So that is what is actually I wanted to say. And one more thing is the angle of attack. So if you consider this as your direction of wind, let's say this is a wind direction, and this is your chord. So the angle between this wind direction as well as that of the chord is actually called as your angle of attack. So higher the angle of attack, the greater will be the lift force. So the greater is the lift force, you will be having more amount of the wind power that actually gets generated from your windmills. So this thickness to the chord length ratio as well as the angle of attack should be higher. So if in this case if it is higher, then what happens is the lift force, that is nothing but the force acting in a direction perpendicular to the airflow will be greater, and that will help in generating more amount of wind power. So more is the wind power, so you will be able to generate or harness more amount of energy, electrical energy from the system. So that is the concept of actually your angle of attack and the blades which are assumed or which are assumed to be modeled as a airfoil. So let me just write here. So horizontal, the basis of classification is the rotor axis is in the horizontal direction, is horizontal, and parallel to the direction of the wind stream, and vertical is nothing but the rotor axis is vertical and perpendicular to the wind stream as well as the earth surface. That's next question. So we are actually going to use the wind power or the kinetic energy, which is the wind energy, which will actually rotate your blades, and then that rotation of the blade is extracted to be a electrical energy. But the question is, how much amount of the energy is going to generated, or to be more specific, what should be my speed of the blade or the rotor blade, or what should be the wind speed, so that I basically get this much amount of power. We do not have an idea of what should be actually the wind speed to get this much amount of power. So that is something that we do not really have an understanding. So it is not that whatever amount of wind energy that actually strikes your blade will actually get converted to the electrical energy that you can harness, or how does the wind speed, so what should be the exact wind speed so that this much amount of power gets generated. So we do not have an idea about that. So that is what we will be discussing now. So this curve that you see, it is nothing but it's actually called as a power curve. So what is a power curve? A power curve is nothing but a curve that actually relates the power of your system to the wind speed. So at a different wind speed, how much amount of the power will be generated is what is actually going to come out in your is actually what is represented here. So it's the relation between the power that is generated through the windmill, or that is generated from the windmill, to the wind speed. So here if you see, you have something called as cut-in speed, cut-out speed, rated speed or rated capacity. So that's what we will be discussing now. So cut-in speed is nothing but it's the minimum speed at which the blades actually starts turning. So you need to have a minimum threshold amount of wind energy, right, so that the blade actually starts moving. Suppose like for example, even if you take a toy fan, if you are going to blow air, it's not necessary that at all there should be a minimum amount of threshold value for the toy fan to actually start rotating. So you need to blow certain amount of air for the toy fan to actually start rotating. Similarly, even in case of a windmill, there should be a sufficient amount of the speed of the wind so that the blades actually starts turning, actually start rotating. So that speed is actually called as a cut-in speed. Before that cut-in speed, whatever amount of wind speed is there, that will not be responsible for generating any kind of power to your system, or you cannot generate any kind of power from there. So that is the reason, if you see below this wind speed, the power that is actually getting generated will be zero. There will be no power, because the blades are actually not rotating at that wind speed. The threshold value is not reached. So the amount of force that the wind actually imparts on your blades is not enough to rotate those blades. So when the blades are actually not rotating, so then where will the power be generated? Because as we know, fundamentally, that the blades has to rotate for the electrical energy, for the kinetic energy to basically convert to electrical energy, which we can use it for our application. But when the blade itself is not moving, when my wind speed itself is not able to rotate the blades, then where will the power come from? Where will the electrical energy come from? So that is the reason, if you see below this cut-in speed, the amount of power that is actually can be harnessed, or the wind power that is available to rotate the blade, will be zero. So the cut-in speed is nothing but, it's also, you can call it as a threshold speed for the power generation to actually start. Now after that, you have something called as a rated speed. So what is a rated speed? Rated speed is nothing but it's basically the minimum speed at which the wind will generate the designated power. So if you see, for every kind of equipment you have certain specification, right? Like this much like this particular instrument will operate at this current or this voltage. If you say, if you take any of your electrical or electronic gadgets, or if you say this laptop through which I am actually talking to you, that has a particular specification that it will work in this particular current range, in this voltage range, or some other specification. Like that, even for your windmill, it basically has a designated power range. So that is the power which it can generate. So that will be your that is the specification. So the speed at which it actually generates the designated power is nothing but it's called as your rated speed. So this, if you see the upper limit, this is the rated capacity. So rated capacity is nothing but the designated power, that is how much amount of the power that the instrument can actually generate by the rotation of its blade. So between this cut-in speed and this rated capacity or rated speed, if you see, this power is gradually increasing. So yes, so let's say if your cut-in speed is V0 and the rated speed, that is the speed at which your windmill is going to generate its designated power, is V1. So between this V0 to V1, if you start increasing the wind speed, the blades will start rotating. So once your wind speed crosses your cut-in speed, the blades will start rotating. So once the blade starts to rotate, the energy will start getting generated. You will be able to harness power, electrical energy from there. So as you keep increasing the velocity between V0 to V1 or cut-in speed to rated speed, the energy will keep getting generated. So the curve will start increasing. So that's what you can see. There is a increase in the power generated from the wind as you keep increasing the wind speed. So once after the rated speed, as you keep increasing the wind speed, the power will get stabilized, because that is the designated power that your windmill can actually generate. Beyond that, you cannot actually try to extract the power. It has certain capacity to generate only this much amount of power, and that's what it does. So beyond this, if you increase the speed, if you see here, the power is not actually increasing. It became constant. It got stabilized. So the rated speed is the speed at which you will be able to generate the designated power. Once you keep increasing the wind speed, the power will get stabilized, and there will be no much amount of energy that you can actually harness. But you cannot keep increasing the wind speed as you want, or the wind cannot rotate at whatever speed. I mean, you cannot do that. Like if you do that, then there will be a damage to your system. Assume that windmill can actually rotate only at 50 km per hour, and it has the ability to generate that rated capacity in that 50 km per hour wind speed. But if suppose the wind is actually blowing at 100 km per hour, and that may not be suitable for the system. Of course, we do not know the specification, but just in general, as an example, if you take, if let's say the rated capacity is achievable at 50 km per hour itself, but the wind is actually going to blow at, let's say, 120 or 200 km per hour, then you cannot actually use, like then in that case what happens is, the windmill actually is subjected to get damaged, right? So when the wind speed is going to be blowing at a very high speed, there can be a damage to your windmill or the blades of the system. So that is where the concept of cutout speed comes. So cutout speed is the maximum speed at which your wind can blow. After that, your windmill will stop working, because if it keeps working even after that rain, it may be subjected to a damage. And the windmills are usually very big. If you see the rotor here, I hope you can see the rotor. In the rotor diameter, the blades, they are usually 45 to 40, 43 to 45 meters in diameter, so you can actually assume the length of one single blade. So so if that is going to get damaged, that will incur a huge amount of expenses, huge amount of loss. So in order to replace those blades, there will be a huge amount of investments that would be required, and that is something that we do not want. We want to minimize our costs and maximize our energy production. So if these kind of damages are going to happen frequently, and especially these windmills, if you see, are usually in the coastal region where you can get more amount of wind speed. For example, if you see in the video lecture also, the wind speed intensity will be high in the coastal regions like Gujarat, Rajasthan, Maharashtra, Karnataka, and Tamil Nadu. So you will be able to see the windmills predominantly in these places. So if the wind, and these places are also get a very heavy rainfall, and uh, during the monsoon season, the wind speed will be very high. So if they are going to, let's say, rotate at 150 or 160 kilometer per hour, then they might get damaged. And if this, and since this is subjected to happen year after year, you cannot replace the blades of that windmill year after year, and that will be like a huge burden, financial burden to us. So that's something that we want to avoid. That is why we specify a cutout speed. Beyond the speed, the system, your windmill system, will stop working. So it usually stops working, or it gets shut down by two ways. One is nothing but it's the automatic brakes that is present in your system, and another one is the twists or pitch that is present in the blade. So but using these two mechanisms, once your wind reaches the cutout speed, the windmill system will automatically uh, shut down its operation. So what is the minimum or the appropriate ranges? Is that the cut-in speed should be between 10 to 16 kilometer per hour. So any speed less than this, your windmills will not rotate and no power generation will happen. Cutout speed should be between 72 to 128 kilometer per hour. So any speed more than this will cause a damage to your blades, and the windmill system will get damaged, and there will be a financial loss, and you also need to reinstall that blades. So that will also incur expenditure from your packet. So that may not be what you actually want to happen to yourself. So this is actually called as a power curve, and usually the manufacturer or the people who the manufacturer of the windmill usually give this power curve so that you can actually have an idea on what is the exact cut-in speed and exact cutout speed, what is the rated designated power. All this will come along with the purchase of the windmill. The manufacturer will supply with this power curve during its purchase. So another one concept that comes is the Betz limit. So Betz limit is nothing but it's actually the theoretical maximum amount of energy that can be collected from your windmill or wind rotor. So it is the theoretical maximum amount of energy in the wind that can be collected by the wind rotor. So usually it is not that the entire wind power will be taken up by your blades, and then that will be generating out as an electrical energy. 100% energy is not possible, because what happens is, once all the 100 percentage of the energy actually is getting converted, then the wind will actually stop rotating the blade, because all the velocity that the molecule has will come down to zero. So that is not something that is going to happen in this case. So the maximum theoretical amount of energy that will be generated by the wind will be nothing but it is actually 59% of the wind energy that the wind has. So This is what is proposed by BETS. BETS actually propose that approximately only 59 percentage of the energy can be harnessed from the wind energy. But this 59 percentage is also is a ideal limit. It does not account for any kind of the losses that is actually happening in the system. So once your rotator blade starts rotating, that it has certain amount of losses, and then it is actually going to get transmitted, and then there is a generator, and then there is a storage. So all these will actually start have their own losses. So that was not included when BETS proposed. So BETS proposed is something that is ideal. 59 percentage of the maximum wind energy can be obtained by the windmill system. But once you start incurring all the losses or accounting for every single loss, the amount of energy that you will be getting out will be approximately only 35 percentage. So if you see, the wind is actually rotating at a particular speed, and if you consider that as your 100% energy, it due to all these kind of losses and other system specification, the amount of energy that you will be able to harness will be only 35 percentage. So due to these losses and other kind of system specification, the energy that can be obtained from your wind will be only 35 percentage in your real life. So yes, and the wind power is nothing but is usually expressed by this formula, that is nothing but rho times A times your velocity cube by 2. So rho is nothing but is the density of the air, because air is what is actually going to rotate your turbine blades or rotors. So its density, the area of the rotor, and V is nothing but is the velocity with which your wind is going to rotate the blade. So or the wind speed, that is your V, and that divided by 2. So if you see here, the wind power is nothing but it's actually a function of 3 different parameters, right? One is nothing but your density, and another one is the A, that is the area of the rotor, as I said now, and another one is the nothing but it is your V. V is the free stream velocity, or in simple terms, it's the wind speed at which your wind blows, the speed at which your wind blows, that is the wind speed. So if your air is heavier, if your air is denser, and if your rotor is big, that is the diameter of the rotor is big, and if the wind is actually flowing at a high speed, then the amount of wind power that is available in the wind will be larger, it will be more. So yes, yeah, so of course this has a certain limit. You cannot have a very big rotor, or the wind cannot actually blow at a extremely very high speed like 160 or 170 kilometers per hour. They have their own specification, but as you keep increasing the area of the rotor and your velocity, your power generation will be high. The density of the air is something that is you cannot control on your own. It is something that is subjected to atmospheric variations. So but of course, if you consider a humid air, they will be kind of more dense due to the presence of water molecules. So wind power will be more. But area and the area is under your control. So if you keep increasing the area up to a specific limit, the wind power that gets generated will be more. And velocity also, below the cutout speed, you can actually keep increasing and you will be able to generate more power. So this is the formula, and it is usually expressed, the wind power is usually expressed in terms of watts or kilowatts, depending upon the specification. Usually it will be in terms of kilowatt because that much amount of power will be the wind will be having, so that we can at least harness 35 percentage of it. So yes, it will be usually expressed in either watts or kilowatts. Next we actually move. So here I told the Betz limit is nothing but it's actually 59 percentage of your wind power. But how did this actually get formulated? How did Betz actually came up with this term of 59 percentage? That is what we will be looking through for the next for the rest of the time. This is nothing but he used actually the 1D momentum theory, or so called as the linear momentum theory, for the what do you say explanation, or through this model he was able to conclude that 59 percentage of the maximum energy could only be harnessed. So if in case if you have any doubts in these two slides, then you are welcome to ask me now. Do you have any doubts? No. Okay. So before we move on, so this will be quite complicated because this usually includes terms like something more related to mechanical aspects. So let's try to understand every like the terms, so that it will be clear to you at least to a greater extent. So if you see this 1D momentum theory, or it's actually the 1D model of this is actually based on the linear momentum theory. So here we have assumed like taken a control volume, like that is the place where we are actually, in a simple terms, that is actually where we are going to describe about the variables that we are interested in. We are going to take a certain element in the entire flow, in the entire flow of your wind and then the turbine. We actually take a very specific portion. So your wind will be flowing in this direction 1, and it will be moving out in your direction 4. So in both these places, V1 and V4, they will be equal. So that both V1 and V4 will be equal to your wind speed, the free stream velocity, the speed at which the wind comes or the wind blows. Let me just write that. But it's your free stream velocity of the air, or you can say the speed at which your wind blows. So between these two, this place, the 2 and 3, is what is your rotor blade is actually present. It is the Betz actually proposed that there is proposed, or basically considered this model as an actuated disk model, and with this actuated disk model he was able to propose the concept and the different parameters, and how the what do you say the wind power rotor performance is nothing but is like 0.5 or 59 percentage, or 0.59 times of the wind power that is available. So this model usually has certain assumptions. So here they actually consider it is to be homogeneous. The air should be homogeneous mixture, and then it should be incompressible. What actually incompressible means is that the density of the air should not be a function of temperature or pressure. That is, it should not be, that is, incompressible means unable to compress. You cannot compress, that is what is incompressible. So the fluid or the air molecules that you take, the gas, the air, should be incompressible, should not be compressible. What it actually means is that its density should not be a function of temperature as well as pressure. It should remain constant, like depending upon the temperature or the pressure, your density of the wind should not actually change. Then a steady state fluid flow is assumed, that is the air molecules that is actually passing through your control volume, or this is actually a control volume, a specific element in the airflow regime. So that should be steady state flow. What it actually means is the velocity, the flow, the sorry, the airflow should not actually vary with time. It should not be a function of time. That is the another one assumption. Then you assume that infinite number of blades is present, so you do not, so this model is actually applicable irrespective of the type of wind turbine that you actually consider. It can be single bladed, multi bladed, or horizontal, vertical, but these are the assumptions. So there should be infinite number of blades. Then the thrust over the disc, that is your rotor. So this pressure, this point 2 and 3 is nothing but the rotor will be present. So the rotor, since it's actually round, you actually take it as in the form of a disc, and that thrust is nothing but the force that is actually going to act on the rotor or the disc, that is going to be uniform. And you have a non-rotating wake that is getting generated. So wake is nothing but when there is a kind of a disturbance to your wind or airflow, there will be a wake that gets generated. This wake actually decreases or reduces the amount of energy. So that is usually rotating in nature. The wake is actually rotating in nature. I mean, it has both rotating and non-rotating, but the rotating wake actually decreases the energy that can be harnessed. So the wake that is getting generated is assumed to be non-rotating. And another one assumption that we take is the static pressure far upstream. So this place between 1 and 2 is the upstream flow of air molecules. So this will be your upstream, and between 3 and 4 it will be your downstream of air. So the static pressure far upstream, that is at your point 1, is and far downstream, that is your point 4, are equal, and they are equal to the undisturbed ambient static pressure, that is nothing but your ambient pressure. So you can also write this. So your P1, P is nothing but the pressure, and your P4 or the pressure at point 4 is equal to P atmosphere. So this is another one assumption. So the pressure at the point 1 and point 4 are equal to that of the static atmospheric pressure, which actually means that the disc or the rotating blades actually do not have an effect, because they will have an effect on the wind speed or that pressure in the air molecules only up to a certain distance, right? So if you keep if you go far away from that rotor or the disc, you cannot actually feel that pressure. So that is the reason this point 1 and point 4 are considered very far away, so that their pressures are actually equal. In case if you are unable to understand any terms, then you can let me know, because there are multiple terms here: incompressible, steady state, thrust, and yeah. So if you are unable to understand, then do let me know. Basically, this model is actually used to describe, or is used for actually calculating how the wind turbine rotor performance. So we actually proposed here, right, that the Betz limit is nothing but 59 percentage of the wind power. So how does that actually comes is what we actually discuss here. Using this theory only, Betz actually proposed that the wind turbine, or the amount of energy or the power that the wind turbine can harness, is nothing but 59 percentage of the power available in the wind. So if you see here, the linear momentum theorem actually states that the net force on this control volume, that is in this entire control volume, if you take between this 0.1 and 0.4, the net force that is acting on the system is equal to the thrust force on the of the wind on the wind turbine. That is the amount of wind, that is what pressure the wind is going to apply onto the wind turbine. Both are actually equal. So there is a whole lot of, what do you call, derivation that is available in the video lecture, since we have to actually solve some problems also for today's discussion and discuss some other concepts also. I have not I am not going to explain the derivation or do the derivation. Professor Anandalakshmi ma'am has actually derived it in the video lectures. You are always welcome to check that. Here our focus will be to see specific points, important points about the model, so that it will be helpful for us for solving the numerical questions. So according to the linear momentum theorem, the very basic, the linear momentum theorem, the net force on your control volume should be equal to the thrust force of the wind on the wind surface. Of course, when I say a linear momentum theorem or a 1D momentum theorem, there are also 2D momentum theorem and 3D momentum theorem. But here we are not, here we are not going to discuss all those stuffs, because our discussion is only focused to the linear momentum theorem. So based on this linear momentum theorem and derivation, we actually obtain these equations. So first is nothing but is the axial thrust on the disk. Axial thrust is nothing but the thrust in the direction of the axis. That is, this is the axis direction, the flow direction. In that direction, what is the thrust or the force that is going to be applied onto your disk? So that is expressed as rho a v cube by 2 into 4a times 1 minus a. So the a is nothing but it is actually your axial induction factor, which is described as v1 minus v2 by v1. So v1 minus v2, here is your v1, that v1 is nothing but it's actually your speed at which the wind blows, you can take that as u. v2 is nothing but the speed at which the wind actually starts rotating the blade, and that ratio is actually called as the axial induction factor. So based on this, you can get the axial thrust on the disk. So after this, you get after you get these two, you will be able to calculate the wind turbine rotor performance. That is nothing but P out by P win. So P out is nothing but, or P out in the sense, the P of the rotor. So what is the power that I can harness, or what is the power that is going to get generated from the router to the power that is available in the wind. Power available in the wind we have calculated here, wind power, that is rho a v cube by 2. So this is P into a into v cube by 2. So since we know the axial thrust on the disk, so you will be able to calculate the power, that is the P rotor. Let me just write it as rotor for for understanding purpose, P rotor. Yeah. So since you know the axial thrust on the disk, you will be able to calculate the P rotor, power of the rotor. So power of the rotor divided by rho a V cube by 2 will be nothing but 4a times 1 minus a cube. So this wind turbine rotor performance is also expressed in terms of the coefficient called Cp. Yes, so Cp is nothing but 4a times 1 minus a square. A is nothing but is your axial induction factor. And to calculate the Cp max, or what is the maximum wind turbine rotor performance, you have to like what do you say, differentiate this Cp with respect to A, and then from there you will be able to calculate. So if you differentiate, you will be getting the value of A as 1 by 3, and if you substitute here, you can get the Cp max as 16 by 27. Let me just show it here. So to calculate the maximum of any quantity, the procedure is you need to differentiate that particular quantity with respect to the variable that you have in the equation. So dou Cp by dou A should be equal to 0. So if you do that, you will be getting the value of A as 1 by 3. So let me just show that. So d by dA of 4a times 1 minus a So if you do this, you will be getting the value of a as 1 by 3. You can actually, this derivation is also given in the video lecture, so you can actually go through that. So the Cp value will be nothing but 4 times 1 by 3 1 by 3 whole square. So if you calculate this, if you do this and then if you equate it to 0, you will be able to get the value of A, that is 1 by 3, and then the Cp value will be 16 by 27, and this Cp is nothing but the Cp max. So this will be the maximum amount of the maximum wind turbine rotor performance, and 16 by 27 is nothing but 0.593. So yeah. So that is what is actually given here. Cp max is 16 by 27. So this is called as a Betz limit, and that is nothing but 0.593. Betz limit. Yes. So if you have any questions, then let me know. Or we can actually go on towards solving problems. I can understand these two things are actually quite complicated because it involves a lot of terms which may be new to you. So that's the reason I have not went on towards discussing the derivation, because that involves all this Bernoulli's equation, the energy conversion equation and stuff. So that may not be comfortable for everybody. So that is the reason I am not discussing that here. So if you don't have any doubts, then I think we can actually go on towards solving questions. So this is your first question. It says that in a coastal region the wind is actually blowing at a speed of 50 km per hour and the diameter of the rotor is given as 60 meter. Now they are asking you to calculate the wind power and they are asking you to assume the temperature and the pressure in the coastal region as 288 Kelvin and 100 kilopascal. So how do you solve this? How to calculate the wind power? What is actually the wind power? So the kinetic energy is what is kinetic energy that is present in the wind of the air molecules is what you are going to get as a wind power, right? So how to calculate this? Any ideas? So I'll give you some time for you to think so that we can, in case if you find it difficult, then we can actually go for solving the problem. It's very simple. Everything is given, you are just asked to substitute. So the question is how do you actually calculate the wind power? What is the formula for the wind power? What is the formula for the wind power? Wind power formula. So let's just start. Like I'll not be solving it now. Let's just see how does the wind power actually come. Like I mean, how do you actually get the expression for wind power? So what is power as such? If you see power, what is actually the power? How do you express power? Power is nothing but energy per time. So how much amount of energy you are going to consume in a certain amount of time is nothing but is called as the power of the system, and mathematically you can write it as dE by dt, that is differential of energy over time. So here the energy that is going to be involved in our process is the kinetic energy of the molecules, of the air molecules. So it can be specifically written as dke by dt. So what is the kinetic energy expression? You can actually say me this is very simple. What is the expression for kinetic energy?
Half mv square.
Yeah. So here your m will not be just mass, it will be your mass flow rate. M is mass flow rate, it will be m dot honestly. So here m is nothing but mass flow rate. So kinetic energy can also be expressed as like, okay, yeah, let me just say, so mass flow rate can also be expressed in terms of density and volume. So since for air you will not be able to calculate the amount of mass, like in the sense you will be knowing the volumetric, like you will be knowing only the velocity of the air, so from there you are supposed to calculate the mass flow rate. So mass is nothing but, so mass flow rate is nothing but mass by time, mass per time, right? or just a second. Let kinetic energy be half mv square. So power is nothing but differential of kinetic energy over time. So that will be 0.5 m v square divided by time. So mass by time is nothing but mass flow rate. It's better, it won't be confusing. So let that mass flow rate be capital M v square. Here m is nothing but mass flow rate. But since we have only the idea or the data for the density of the air and the velocity of the air, so we are supposed to express this mass flow rate in terms of density and velocity. So for that we actually know that mass is nothing but density by volume. Density into volume, right? So mass flow rate will be nothing but mass by time. So mass is nothing but density times volume by time. So which will be nothing but density times volumetric flow rate. That is how much amount of the volume will be flowing in a particular amount of time through a particular area. That is volumetric flow rate. How much amount of the volume will be flowing in a unit amount of time. So volumetric flow rate can be written as area times velocity, area times velocity. So now power is nothing but half of mass flow rate times v square, right? So 0.5 times mass here is nothing but density times mass flow rate is nothing but density times volumetric flow rate, and volumetric flow rate is nothing but area times velocity. So 0.5 times density times velocity times area first times velocity into velocity square. So power can be expressed as density is rho times area is A. This area is nothing but is the area of your rotor, because that is what is actually going to rotate, times velocity into velocity square, so velocity cube by 2 or 0.5. So this is how you actually get the expression for power. So this is the wind power or power available in the wind, or the power that can be generated by the wind. So this is the power, rho into A into V cube by 2. So now with this I think you will be able to calculate the wind power that is available for this question.
Yes.
Yeah, so can you tell me, let me know the answer? Or let me just simplify this question so that assume that it will be easy. Assume that the density is 1.225 kg per meter cube. Actually in the previous if you see the way I framed the question was, assume that the temperature and the pressure of a particular area is this, and then we assume that the air is the ideal gas. That is also mentioned. So if you have those kind of questions, if you see that, if you assume that the air is an ideal gas, and if you have the temperature as well as the pressure, then you can use the ideal gas law, and from there you can actually calculate the density of air. But let's now, for simplicity's sake, let's keep assume that the density as 1.225 kg per meter cube. So now, will you be, I think you will be able to solve the question.
Okay, I'm trying it.
Okay, okay, yeah, sure. So before actually solving this, you are supposed to convert the units, because if you see, the diameter of your rotor is in meters and density is in meters, but your velocity, if you see, or the speed is in kilometer per hour. So you are supposed to change it to meter per second before solving, otherwise the units will not match.
Okay.
So first, what is the wind speed? Like, did anybody calculate?
13.9 meter per second.
How much?
13.9 meter
Yeah,
per second.
yeah, correct. 13.9 meter per second. So you can solve the rest before I explain how we get to that place.
I get the answer as 4637 kilowatt.
Uh, it's actually more like bigger. Did you calculate your area? What was your area?
It's pi r square,
Hmm.
pi into 30 into 30.
Okay.
Okay, and so velocity is one is around 13.9. So I take the cube,
Hmm.
multiply by pi. So
Okay. Okay. Okay.
can I
Yeah.
write?
Yeah. We'll just solve here in the in live. We will solve it here. So you have it in 50 kilometer per hour. So 1 kilometer is nothing but 1000 meters. So 50 into 1000, and 1 hour has totally 3600 seconds, 60 minutes, and each minute 60 seconds, so 3600 seconds. So if you calculate 50 into 1000 divided by 3600, 13.88, or you can take it as 13.9 meter per second. Yeah, that's the same. And your area, so area is nothing but the area of the rotor. So area of the rotor is nothing but pi r square. So pi, 3.14, and r, here you have given the diameter of the rotor as 60. So R will be nothing but 60 by 2, that is 30, and that value will be 2826. Yes. uh, so wind power will be nothing but, with this formula, density we know it as 1.225, so 1.225 times area is 2826 times your VQ, V is 13.9, so 13.9 Q, the whole divided by 2. So let's calculate here. So 13.9 2865.619 is 13.9 Q, 2685.619 times your area, that is 2826, times density, that is 1.225 rho A V cube, the whole divided by 2. So it will be approximately 4648,605 point something.
Yes, yes, same answer.
Okay, so that will be 464, let me just check once, 46486, yeah,
05 watt.
4648605.617 units is watts. So if you express this in kilowatts, it will be 4648.605 kilowatts. So this will be the amount of power that will be available in your wind. So the wind that is actually blowing at the speed of 50 kilometer per hour will be able to, generate power of 4648.605 kilovolt. Sorry, kilowatt. So this, so I hope there is no doubt in this question. It's just that we are actually substituting the formula. Suppose if you are not given the density, like previously as we saw, we were not, I didn't give you the density directly. In that case, you know from the ideal gas law, PV is equal to nRT, and N is nothing but, it's actually the number of moles. N is number of moles. That is equal to M by capital M. M by, I mean mass of your air divided by the molecular weight of your air. Yeah. So if you express this, then you will be able to get getting rho, that is your density, as P, pressure, times M, that is your molecular weight, divided by R times T. So if you are not given the density of the air, then you can use the gas law, ideal gas law. I mean, if it is written that the air can be assumed as an ideal gas, then you can use the ideal gas law, express the N, that is your number of moles, as mass of the air to the molecular weight of the air, and then you can express density as Pm by RT, that is, so PV is equal to small m, that is mass of the air, RT by capital M. So if you take your volume to the other side, it will be P equals mRT by molecular weight of the air times the volume of the air. Mass by volume is density, so P equals rho times R times T divided by the molecular weight of the air. So if you take it to the other side, you will get the density as Pm by RT. So P is pressure, M is the molecular weight of the air, R is your gas constant, and T is the temperature that is given. So you can also do by this way in case if your density is not given. So for simplicity purpose, for solving this question, since it's our very first question in the wind energy, we have taken the density as we took the density as 1.225 kg per meter cube. You can also, if the density is not given, then you can express the density as a function of pressure and temperature, and then you can calculate. Moving on, we have our next question. So the next question is not, so in case if you have any doubts related to this question, then you are please, then you can ask me now. Do you have any doubts? Okay, then okay, yeah, sure, then let me just go to the next question. So here they have asked us, in a flat coastal region, the wind speed at 5 meters is measured to be 10 meter per second. Determine the wind speed at a height of 50 meter per hour. So if you see the wind speed will keep increasing as you actually move up. The reason is because at a lower surface, at a lower altitude, you will have many disturbances towards the flow of the air, the flow of the wind. So due to that, the speed at which the wind actually flows will decrease because of the disturbance. Whereas if you keep going at a higher altitude, the number or the amount of disturbances that will be available will be very less. So when there is no disturbance, the speed of the wind will be more at a higher altitude. So and that expression on how does the wind actually varies with the height is given by this expression: V by V naught is equal to H by H naught times alpha. And the value of alpha will be the alpha is nothing but your surface roughness coefficient. So this value will be different depending upon the geographical location. So for a flat coastal region, if you see, the value of alpha will be 0.143 alpha. This is for a flat coastal region.
Sorry to interrupt you, sir. Sir, this is A or alpha, sir?
Like here for like, I mean, okay, we will just insert the variable because
Okay, sir. So if this is alpha, so in assignment there have a question alpha in attack angle. Just like alpha is the attack angle in
oh
coastal
that
area. So
if you
what is the difference?
okay, that is angle of attack. So that alpha is nothing but it's actually, if you see, let me open the Jamboard. So this, if can you see the Jamboard here? So here if you see, this is the airfoil and you have a chord in the airfoil. This is your chord and this is the wind direction, and this is your chord. So the angle between this chord and the wind, this alpha is called as the angle of attack, and that alpha is the surface roughness coefficient. You have two alphas, so one alpha is for the angle of attack and the other alpha is for your surface roughness coefficient, to calculate how does the velocity or the speed of the wind varies at different heights. So here you are going to have two different alphas. So depending upon the question, you can like take the values. Like see, if you see here, only for this question on how does the wind speed actually varies, only for those question, for that question your value of alpha will be surface roughness coefficient. And if they are going to talk about the wind direction and then your chord length airfoil, that will be your angle of attack. So here this alpha is nothing but it's called as the surface roughness coefficient, and the value of alpha is 0.143 for a flat coastal region. Like that, for a sheltered region, if you see, the value of alpha is around 0.25. So these are the values of alpha, and with this you can actually calculate the velocity or the wind speed at a height of 50 meters. It just you need to plug in these values into your expression and you're able to get that difference, right? So one alpha is for the surface roughness coefficient, and then the other alpha is for the angle of attack. Angle of attack is nothing but it's the angle between your wind direction and then the chord length, and this alpha is for your surface roughness coefficient. That is how does the wind velocity varies as a function of height. So with this you can actually solve the equation now. So if you just plug in these values, then let's see how the wind is going to vary with the height. So V is what we are supposed to identify. V is the velocity at that altitude, velocity at a particular altitude. And your V naught is the velocity that is given to you. You can take at a known height, or you can take known velocity at a known height. This is unknown velocity. The capital V is unknown velocity to be calculated at a particular height. So here V will be the velocity that we want to get at a height of 50 meters. V naught is the velocity, the known velocity at a known height. So that will be 10 meter per second for a height of 5 meters. So h will be the height where you want to calculate the velocity. And h naught will be the height at you can say the initial height or height where you know the velocity. So you have four different. One is V, where you are supposed to calculate the velocity. One is V naught, where you know the velocity. H, where you actually want to calculate the velocity, and H naught is where you know the velocity. So it's simple. So at 5 meters you know the velocity, that is 10 meter per second. At 50 meters you don't know the velocity. So here your V will be, V is what we want to find. V naught will be 10 meter per second. H naught will be 5. For this 10 meter per second, the height is 5. At a height of 5 meters, the velocity is 10 meter per second. And H, where we want to calculate the velocity, is 50 meters. So it's just you need to plug in the equation. So V by V naught, V naught is 10, is equal to 5 by, sorry, 50 by 5 whole power 0.143. This is a fixed value. For a flat coastal region, alpha value will be 0.143. So V by 10 equal to 50 by 5 is 10 whole power 0.143. So what will be the value? That is 1.3899 or 1.39 you can take it as. So V by 10 is equal to 1.39. So V is nothing but 10 times 1.39. So that will be 13.9 meter per second. So you can see how the value of your velocity or the wind speed is going to increase with your altitude. So as you keep going higher and higher, the wind speed is going to increase, and the major reason why this is actually happening is because as you move up, the amount of disturbances that is actually present in the to your wind will be less. So when the disturbances are going to be low, the speed will be higher. So because once you have disturbance, your wind will actually go and attack the disturbance, or like let's say if this is your disturbance, the wind is actually moving in this direction, and once it encounters the disturbance, some amount of the velocity will actually get decreased before the wind can actually deflect from its path and move to in the other direction. So there is some amount of the energy that is actually going to get lost in this process. So that is the reason the wind speed at a lower altitude is lower compared to higher altitude. At higher altitude, as you move, the wind speed will be more because the amount of disturbances at higher altitudes when you move will be less. So the wind speed will be more. Uh, do, do you have any doubts related to this question?
No, sir. Thank you.
Okay, yeah. So this, as you asked, this there are actually two alphas. One is for the angle of attack, and another one is for the surface roughness coefficient. So yeah, there are actually two different alphas to be here. So it's you need to actually differentiate between the question asked, and based on that you have to interpret the value of alpha. So I will conclude the session here for today. Let me stop presenting my screen.
Okay, sir. Thank you.
Yeah, so okay, if do you have any doubts? In case if you have doubts, then you can let me know now.
Actually, I have doubt in the angle of attack, which is the assignment in question 9. I can't understand this question. That's why
Is it okay? So like I cannot actually tell you the answer for that question. I am not supposed to tell you, but yeah. So but the concept of angle of attack is nothing but it's actually the angle between the chord length and your the wind motion, that is the direction at which your wind is actually blowing, and then the chord length of the airfoil, the blade. So that angle is your chord, what is it called, the angle of attack. So yeah, okay. So I will take up that question for you in the next session, because by the next session the keys will be out, right? So after that I can actually take up and I'll help you with out in the next session. So I'll conclude the session for today. So thank you for thank you for joining the session today for the week 11 live interaction session. I thank both Ananda Lakshmi ma'am as well as Vaibhav Vishant Gaut sir and NPTEL team for giving me this opportunity to interact with you all in this Sunday afternoon from 5 to 7 p.m. So let us meet for our very last live interaction session, that will be on 14th April from same 5 p.m. to 7 p.m. and that will be our last live interaction session for the course Renewable Energy Engineering. Yeah, okay, till then if you have any doubts then you are always welcome to email me. My email ID is given in the presentation and you can also access the recordings through the NPTEL course page. Yeah, if you do not have any doubts then let's conclude the session. Have a happy weekend and yeah, bye.